This is the first lecture on course EE540, which is named Radio Frequency Integrated Circuits. So this lecture is going to be the introductory lecture on this course, where we will try to find out what are the various circuits that we will be discussing under this course by taking up example of a wireless transceiver for voice communication. But before we go into that transceiver architecture, we will start our discussion with the title of this course. And as you can see that the most important word in the title, radio frequency integrated circuit, is the word circuit. So this course is fundamentally about circuits, and we know that circuit is basically a network of passive components, resistors, capacitors, inductors, and semiconductor components like transistors and maybe diodes also. So here we will be considering network of these components. Now the second important word in this title is integrated. So this says that we will be talking about integrated circuits. So it implies that there are different versions of circuits. So if you see circuits, they come in two major versions. One is discrete, and second is what we are going to talk about, integrated. So in the first one, in the discrete circuit, each of the components, see these resistors, capacitors, inductors, and transistors, they all will be individual components and manually interconnected with each other, either on PCB or, for example, even on breadboard. And the size of each of these components, they will be of starting from few millimeter to few centimeters. So the size will be large, and because of this large size, it will be difficult to accommodate a large number of these components on any given area. So if the component number cannot be very large, then the circuit functionality will also be very simple. Only basic functionality can be realized using discrete. So disadvantage is large size, and because each of the components will be exposed to external world, so the interconnect tend to break down, and their reliability is low. So these are the two major disadvantages of discrete circuits. But what we are going to study is integrated circuit, and in the integrated circuit, which in short is called ICs, same components, these resistors, capacitors, inductor, transistors, they all will be fabricated on the same piece of semiconductor where transistor is fabricated. So all the components, they are going to be very small, and they will be interconnected and then packaged so that we only have access to the input and output pins, in addition to, of course, the DC supply that will be required. And that makes the circuit more rugged. And because we can have more number of functionality, so the versatility of circuit will also be very high. The idea appears very simple. That means you just interconnect all the components on a same piece of semiconductor. But the idea is so important that the person who first successfully created these integrated circuit, Jack Kilby, in 1958, along with Robert Noyce, who later on founded Intel. He was awarded a Physics Nobel Prize in 2000. And this idea of integration played major role in revolutionizing the electronic industry. Now, the third important phrase that appears in the title is radio frequency. RF in short. So actually there is no rigorous definition of the band which can be called radio frequency. But for our case, for this course, we will typically mean a frequency band from few megahertz to few gigahertz. However, there could be people who might say that this band actually extends up to tens of gigahertz or even more also. But those frequencies, they typically fall in a band called microwave band. Which is very well defined, starting from 300 megahertz to 300 gigahertz. So unlike microwave, RF frequencies or radio frequencies are not very well defined. So this is about the title, but as was pointed out in the circuit, whether in discrete form or integrated form, the one of the key components is going to be transistors. So we know that these transistors, they are implemented in two different versions. One is where only single type of charge carriers are involved. They are called MOS, MOSFET or JFET. And second, where both types of charge carriers are involved, they are called bipolar junction transistors, BJTs. So many of the circuits, they can be implemented either using MOS or using BJT. Since these days, almost all the digital circuits, they are implemented using MOS, and this fabrication technology is readily available. So even the RF circuits, RFICs, they are also implemented using MOS. So what exactly we are going to study is MOS-based RFICs. That means we are going to study CMOS RFIC. CMOS means complementary MOS, and by CMOS here we mean that we use the same fabrication technology that is used for CMOS digital ICs where both PMOS and NMOS are used. That is why complementary MOS. Now to understand that what are the different types of circuits that we are going to study, we will have to look at architecture of a wireless communication system for voice communication. So we know that uh, any wireless communication system involves both transmitter and receiver. So if you see the simplest architecture, then actually there will be very few components. So we will have a microphone which will convert voice into electrical signal. That means either voltage or current. And then this can be ideally fed to antenna. But because the strength of this wire and the current produced is going to be very small, so we need circuitry. Not only that, the frequency of these electrical signals, they are going to be very low, of maximum of 20 kilohertz, so that will lead to large antenna size. And another disadvantage of connecting this thing directly to antenna is going to be that the receiver, the person who's intended to receive this voice, will not only receive this voice, but voice transmitted by all other transmitter in the locality, same locality. That means all the voice signals, they are going to be confined to up to 20 kilohertz. So to reduce the size of antenna and to uh, separate each user from others so that the receiver receives only one specific user, and also to amplify these quantities, we need to uh, put a set of circuits between this microphone and antenna. So we will see shortly what are these circuits. So this is the transmitter path. And once the signal is transmitted, it will be received and it can be finally fed to speaker. But before it is fed to speaker, again it has to pass through a set of circuits which will segregate the user that we want to listen to, and also to amplify the signal suitably so that speaker can produce sufficient amount of volume. So we again have set of circuits here. So this is the receiver path. Now to see what are the components that will be there in these two blocks, we will draw the more detailed architecture of this transceiver. And that will also reveal us what are the various circuits that we will be studying in this course. So antenna part we have already seen. So antenna is of course going to be there. And now we see that there are two paths, one for the reception and another for transmission. So here we can see that we have now a number of blocks, and it is these blocks that we had earlier shown here as a black box. So now we have separated them out in different color to point to the different uh, topic that they will be usually covered under. So here we see that when signal is received by antenna, electromagnetic wave, the voltage or current that it produces is sensed by an amplifier which is called LNA, low noise amplifier. And then this is then processed by this block which is called mixer. And in the transmitter path, we see that signal is again fed to a mixer and then fed to another amplifier which is called power amplifier, and then finally to antenna. So here we see that we have another block which is feeding to these two mixers, and this block is oscillator or frequency synthesizer. So we have these block 1, block 2, block 3, 2 is again here, and this block 4 and block 5. So block 4 and 5, they are fundamentally doing the same thing. That means providing a periodic signal to mixer in both the path, transmitter and receiver. Now in addition to this, we have here analog to digital converter, and then DSP block, and then finally digital to analog converter, because the signal which should be fed to speaker should be analog, meant to be produced in the real life. So all the signal that we sense in real life or is produced in real life, they are of analog nature. So in the transmitter path, we have reverse scenario. This analog voice is converted into digital, then processed by DSP, and then finally digital to analog converter is there, and then fed to a set of other circuitry. So here in this architecture, these are the mixed signal or DSP circuitry, and this speaker and microphone, they are called transducer because they either sense or produce mechanical signal, and on the other side they deal with electrical signal. While all these things that we have shown here in blue color is actually set of RFICs. So what we will be studying in this course is set up these 5 circuits that has been shown here. And these RFIC circuits, they are also called front end circuit. Because here you can see that immediately after the antenna, we have these sets of circuits. So antenna is the interface between real world and the circuitry. And this antenna is always a passive element in most of the scenario. And after that, we have these active circuit. That means circuit consisting of transistors. But what I have shown here is sufficient detail, not the full detail of the architecture. There will be various other components. For example, filters will be there located at input and output of these amplifiers and at subsequent stages also. Similarly, there will be a power divider or coupler, which will ensure that transmitted signal goes to the antenna, not to the receiver path. Similarly, received signal goes towards receiver, not to the transmitter path. So those components we will not discuss. We will discuss only these 5 components shown in this architecture. Now we are going to talk in a little bit more detail about these 5 components. So first one is low noise amplifier, or LNA. So we see that immediately after the antenna, there is an amplifier in the receiver path, and this is called LNA. So here you can see that this circuit is fundamentally an amplifier. That means whatever input voltage it is receiving, it is amplifying and producing on the output side. So why we have this low noise connected with this amplifier? Because here the received signal or the received power is going to be very small, of milliwatt order or even small. Similarly, received voltage is going to be of microvolt. So this signal is already very low, and if amplifier adds lot of noise, which will inevitably happen, we cannot prevent an amplifier from adding noise to the input signal. So this output will become a lot more noisy, and then it will become difficult to process it. So it is important that this amplifier does not add a lot of noise to the incoming signal. So that is why we have to uh, focus on the noise added by the amplifier to the incoming signal. And when we analyze this circuit in this lecture, we will see that we will pay a lot of attention to this property of the amplifier. So fundamentally, the nature of the amplifier that we will discuss in this LNA are not going to be different from the amplifiers that we have already studied in analog integrated circuits. But here we will be paying more attention to the noise behavior of the amplifier. And to characterize or to compare one amplifier, one LNA with another LNA, and to figure out which one is better as LNA, we use a parameter called noise factor, or in decibel, this will be called as noise figure. So we will take up various LNA circuits and we will find out noise factor and see that which one is better as LNA. Now the second circuit is mixer. So here it was pointed out that actually we could have directly connected this to the antenna and speaker to antenna, but they are to separate one user from another so that the receiver does not hear everyone. We need to put certain circuitry. So here we have mixers both in transmitter path and in the receiver path. So key goal of or the key objective of this mixer is to what is called frequency translate the incoming signal and before it is fed to antenna. So it fulfills two objectives. It increases the frequency that is fed to antenna, so antenna size can be small, and at the same time it also puts every user at different frequency location so that the receiver will be able to easily segregate the desired uh, signal or the desired transmitter from the other one. So what it does is that it, of course, takes the incoming frequency, but then it produces output frequency which is unique for usership for user number one, and it does this frequency translation, frequency shifting, or it is called up conversion also, because the frequency of output is greater than the input frequency. So this is accomplished with the help of another frequency which is fed to this mixer, and this frequency is produced by the local oscillator. So we have a user producing Fi, and then local oscillator producing FLO1, and these two will then produce a frequency which will be different for every user. And this mixer, we will see later on, typically produces a pair of frequencies which will be FLO1 plus minus Fi. So there will always be this pair of frequency at the output of mixer. And here this plus sign is taken for the transmitter path, and this negative sign is taken for receiver path. So we say that mixer does the up conversion in the transmitter path, and it does the down conversion in the receiver path. So in the receiver path, it has to, of course, bring down the received frequency, which is very high, to baseband. That means between few hertz to 20 kilohertz, where the actual voice signal is located. So now from here, we move to third block, which is the power amplifier. So we saw that in the transmitter path, immediately before the antenna, we have an amplifier, and this is called power amplifier. So here also we again find that this is fundamentally an amplifier, but we have an adjective power. So it says that the role or the parameter related with this amplifier are going to be different compared with that of LNA. This power amplifier takes input power and produces an output power, and this output power is finally fed to the antenna. So if more power is fed to the antenna, then this is going to produce electromagnetic wave which will be stronger, and the receiver, even if it is a larger distance from this transmitter antenna, it will be able to receive the signal quite well. So we find that the distance of communication or the distance of transmission, which is dependent upon the strength of this electromagnetic wave, in turn is dependent upon the output power produced by the amplifier. So if we have more output power, there will be stronger electromagnetic wave, and the distance of communication or reception will be also more. So by simply having a stronger or more powerful power amplifier, we can increase the distance of communication. So this power amplifier has to produce a lot of output power, and it does this by drawing input power from the supply. So for handheld device, it is going to be a DC supply. So it takes a significant amount of input power from the supply and produces a lot of output power. to be fed to the antenna. So here we have a circuit which handles a lot of power. That means it draws a lot of supply power. So wherever any system handles a lot of power, whether electrical or electronics or mechanical, the main issue that arises there is heat generation. And this heat generated then leads to two issues. One is, of course, that you will have to find out a way of dissipating the heat. That is extracting the heat generated in the system. And this will require installing additional hardware cooling system, which will incur additional cost, and it will also increase the size of the system. And wherever a lot of heat is generated, it reduces the life of the system. For example, here of the power amplifier, or in other words, it reduces reliability. So these are the two undesired consequences of the heat generation in a system where a lot of power is handled. So this heat gets generated because not all the power that is drawn from the supply gets converted into the output power by the amplifier. So as a designer or even as a user, what we are interested in power amplifier, which is very good at converting this input power into the output power. That means a system with high efficiency. So we want system which has high efficiency so that these two can be eliminated. And the low efficiency system will have another disadvantage, especially for battery powered system, that battery will get discharged very quickly. So that is why we don't want low efficiency system. And another disadvantage of poor efficiency or low efficiency system will be, even if it is not battery driven, is that it will consume lot of power to achieve same objective. That means electricity bill will be high. So low efficiency implies two disadvantage. One is low battery life, and second is if it is not battery driven, then more electricity charges. So that is why when we study this power amplifier, we will try to analyze the power amplifier with respect to efficiency. Here, this input power that will be fed to amplifier will already be large because it is coming from microphone, and it can be amplified before being fed to the power amplifier. So here signal is going to be large. So we won't have to worry much about the noise added by this amplifier, which it will inevitably do. So that is why noise aspect of this amplifier is not uh, much concern to us or to user or to designer also. Now we go to the fourth circuit or fourth block in the transceiver, that is oscillator. So oscillator is a circuit which produces a periodic output. So there will be output which will be of frequency FOL from the local oscillator. And we have already seen that this signal will be fed to the mixer, which will then translate the signal either in up direction or in the low direction. In the receiver path, in the low direction, that is towards the lower frequency, and towards the high frequency in the transmitter path. And of course, it takes no input. Now the fifth circuit is frequency synthesizer. So as the name suggests, this also produces or synthesizes frequency. That means periodic signal. So it synthesizes frequency. That means periodic signal. So this is also a circuit which produces periodic output. But unlike oscillator, we will see later on that it requires a periodic input of fixed frequency. This need not be variable. But here at the output side, we will be able to change this output frequency using input. So here, of course, this circuit is going to be a little bit more complicated compared with an oscillator. So here, actually, if you see this block, there will be four blocks inside this frequency synthesizer. So here we have our external reference signal, and here we will be getting our output. And we will be able to change this output frequency with the help of block, which is called divide by n block. And this output will be actually produced by, again, an oscillator. But then this oscillator is called voltage control oscillator. That means oscillator which will be controlled by input, and this input voltage is here. So what will happen is that it will produce this output which will be dependent upon this input voltage. And in this circuit, what actually gets implemented is that this output will always be n times the reference frequency. So here you can see that we will be able to achieve uh, theoretically whatever frequency we want, but for any given circuit, there will be range over which the output can be varied, not over the all possible range. And it does by processing this input signal with the help of block, first block, which is called phase detector. Then here we have loop filter. And this circuit, you can see that it has a loop here. And based on the functionality, this circuit is called phase lock loop. PLL. And based on what it does, it is called frequency synthesizer. So these are the five circuits that we will study in this course. Now we will talk about standard impedance, which is used in RF and microwave domain in circuits also. And this impedance is 50 ohm. So what is the meaning of standard impedance? That means all the circuits, they will have their input or output impedance equal to 50 ohm. So here question arises that why we have 50, why not something else? And why all these impedances, first thing is why they all have to be equal, and that why that number has to be 50. So there are two questions that we had to answer. So why all the impedances are same, and why that number has to be is 50 ohm. So we will try to answer this one first. So for that, we will take the example of low noise amplifier or even that of power amplifier, because both are connected to the antenna, which is an external unit apart from the IC. It is not on the IC. So if you take the example of LNA, so here we have our antenna, and this antenna will be then connected to LNA. And this connection, especially for base station, is going to involve a cable, long cable. And this cable is called coaxial cable. So let us see this coaxial cable in a little bit more detail. So it has two concentric cylinders, cylindrical conductors. So one is this outer conductor, which has radius say equal to B, and then we have inner conductor of radius A. So it is this type of cable which will be used to connect antenna and LNA. Now this cable is characterized by an impedance called characteristic impedance. Designated as Z0, and this is actually ratio of the voltage which is say traveling in this direction to the current which is also traveling in this direction. That means forward traveling voltage or forward traveling current. And for any given specific geometry, or that means dimension of this coaxial cable, this will turn out to be 2 by 1 by 2 pi 2 mu by epsilon ln b by e. So what we want from this cable is typically these two things. First is that whatever input power I am giving, I should get ideally same output power. That means there should not be no loss. But that is impossible in real life because of the finite conductivity of this outer and inner conductor. There will be power consumption, and this dielectric that exists between these two conductors, that will also lead to certain loss. But anyway, ideally what we want is no loss. So first requirement from this coaxial cable is at least in real life, low loss. That means difference between P out and P min is as less as possible. Second requirement is that we should be able to send as much input power as we want, ideally infinite power, and that is called power handling. So these are the two typical requirements that we expect from a coaxial cable. So why we have this power handling constraint, or why it will not be able to allow any amount of power to pass through this coaxial cable in real life, is that whenever RF signal goes through this coaxial cable, there will be electric field between the inner and outer conductor. So if the input power goes up, this electric field strength will go up, and then there will be dielectric background. That means current will start flowing from inner to outer conductor instead of going in lateral direction along the axis. So there will be a lot of heat generation because we have dielectric inside it. There will be sudden lot of power loss, and that is not desirable. So this power handling term comes because of the dielectric breakdown of the filling material between inner and outer conductor. So now we want a coaxial cable where we can have ideally very low or ideally no loss and infinite power handling capacity, but that does not happen in real life. So what we will have to do is we have to find out compromise between these two. So let us first see the low loss behavior of the cable. So here it turns out that if we plot the characteristic impedance on x-axis and the loss per meter on the y-axis, then we have a curve which looks something like this. Yeah. That means it attains minimum loss for characteristic impedance of 77 ohm. So for low loss, and I should point out that this is for air core. That means the dielectric between outer and inner conductor is air. Now, if you see the power handling, again, with respect to the characteristic impedance for same coaxial cable, then we have this kind of plot. So its maximum occurs at 30 ohm. So we see that for maximum power handling, for real life cable, impedance should be 30. For low loss, it should be 77. So obviously we cannot achieve both the requirement. So it was decided to choose a number between these two. So arithmetic mean of those two numbers is 53.5, and geometric mean of those two numbers is 48. So 50 ohm was chosen as a value, which gives a good power handling as well as low loss. So this explanation answers that why 50 ohm, why not 100, or why not 10, or why not something else. Now question comes that why all the impedances should be 50. So here you see that this coaxial cable, it will be characterized by characteristic impedance 50. So now if at this interface we have LNA which also has 50 ohm, then what will happen is maximum power will get transferred from here to the LNA, max power, and when the two impedances are same, there will be no reflection also. So no reflection. So both these requirements get fulfilled if we ensure that these two impedances, they are same. So same thing will happen here also. We already have this 50 ohm. And if we have antenna which is also 50 ohm, so same advantage, maximum power from here to here, and no reflection will take place. So, so why all the impedances have to be same, equal, is for this purpose and for no reflection. And why that number has to be 50? It is because coaxial cable with characteristic impedance 50 offers a good compromise for low loss and uh, maximum power handling capacity. Now coming to textbook, there are two textbooks that we'll follow, but they are actually going to be more, but two key textbook that we'll follow are this RF Microelectronics by Behzad, Razavi, and the design of CMOS RFICs by Thomas H. Lee.